Yeah. And in between, I'm gonna play some song corresponding to the topic. Okay, so our first topic is this. Here, Google Maps, it won't do you a bit of good to read. You man, it's so simple, so very simple. Like only a child can do it. Okay, so that means it's gonna be very simple. So we're gonna start. We're gonna divide the topic into four. First of all, we're gonna talk about some basic logics, basic set theory, basic category theory, and then we're going to construct set theory from category theory. That's what we're gonna do. Okay, first of all, a mathematician, when they work, they define things to be very well defined. That means there is no ambiguity. You are very sure of what you're saying. So first of all, what do you think about mathematics? Does anyone have any idea like what is mathematics? What are we doing?
It's taking real world patterns and abstracting.
Okay, so it's patterns and abstract. Any other idea? Because most of people think math is a bunch of equations, a bunch of calculations, integrals. Is that math? Any other idea? So it's patterns and abstraction. Yeah. So for me, I think math sometimes is a language or as a reasoning, a deductive reasoning, and it's not a deductive reasoning, but a deductive logical reasoning. So you start from beginning from something that you assume that is true. We call them axiom, and then from that you derive every other statement. I don't think if anyone agrees with that. Yeah. So that's one definition. Math is a big area. There is pure math and applied math. So first of all, we're gonna talk about logic. So what we need first is like, because in everything we do, we can assess statements like we're gonna tell a proposition. And we say a proposition is just a statement, but is false or true. So everything in math can apply on that, like what is true and what is false. But since there is no universal truth, but what we believe true is from something we start from axiom. So what do we mean about axiom? Is self-evidently or accepted to be true statements. So we start with those things. It's like a belief, like I believe in God. You cannot prove like is God exist or not. You cannot prove that, but you just believe. So axiom is like something you accept, but it is true. Okay, and then from the axiom, there is a tautology. So tautology is a statement, but is true by virtue of the logical form. So we can derive them from the axiom, but they are always true. So it's like you present a truth table, and the result of the truth table is always true. Yeah, and then a theorem. Yeah, the thing here, the aim of this is to define a language, but we are going to accept. That means there is no argument between us, but this thing is true or false. So we have the same language. So first of all, we start from the axiom, then tautology and theorem. A theorem is actually the last members of a finite sequence of formula, which formula is ever an axiom or a tautology. So that means we derive our theorem from the axiom, and it must be a result from the axiom or the tautology. So our first theorem is every theorem is a tautology. That means every theorem is always true. And the proof is like So how to prove or proof rules, we need to talk about that first. So to prove things, so in logic, what we have is like to prove things, we believe we call mode disponent something like this. We believe that f is true, and f for two statements, f is true and f implies g is true, then g is true. Yeah, don't worry about the notation. So this means f is true and f implies g is true, then j is true. So that is the way we prove things. So we call this mode disponents, and the proof of the tautology of every theorem is a tautology. It's just since every theorem can be derived from the axiom, and these mode disponents preserve tautology. So it's just a proof, and we can say that every tautology is a theorem that needs a completeness theorem to prove that. So I think that is the basic things I need to talk, like how to prove things. That means if we have two statements such that we have this form like f is true, like j is true, then j is true. So now let's talk about set theory. Like it's a basic set theory. Okay. Maybe I'm going to talk about a paradox first. So I live in the pier, actually, I live in the pier, and here is my statements. Anyone lives in the pier are liar. Okay, so I live in the pier. Am I lying? You can answer. Okay.
You are.
Okay.
If you're lying.
So you are not lying.
Okay. What's happened there? Can you answer to that question?
If you're lying, then, well, anyone can do this.
And I live in the pier.
So you are lying.
The opposite of tautology, something that it can't.
Yeah. Yeah, because every statement is a tautology or a contradiction. Yeah. So what we have here is a paradox, because you don't know. Because if I'm lying, then anyone in the pier not a liar, but I mean, if I'm lying, then I'm not lying. But if I'm not lying, then I'm a liar. Then I'm lying. So yeah, we don't know. It's not like that. And let's see other things like suppose but the chief, let's consider a chief, cooks for everyone in town, except for all those who cooks for themselves. Who cooks for the chef? Any idea? Yeah, so the chef cooks for everyone in town, except for those who cook for themselves. So the question is, who cooks for the chef?
Does he not live in town?
Yeah, because if he's not living in town, that's gonna be good answer. Yeah, so yeah, if the chef cooks for himself, that means he does not cook for himself. But if he cooks for himself, that means yeah. We're not lost. Yeah. So there is our starting point of set theory. Actually, set theory is founded by Cantor. He is from harmonical. I think it's like harmonical, like Fourier series. That's what he did. And he had some big trouble, and he found set theory, and he believed that a set. So, what do you think about the set first in an entity way? Just intuition. What is a set?
Collection of objects.
Okay, collection of objects, yeah, with some property. So that they believe before this paradox we call Russell paradox. So F is a collection of object X with a property Px. Yeah. But then Russell think about it like, is there any set of every set? The set of all sets, does that exist? Then we have like, first of all, we have, can we have a set but containing himself? How to construct that set? Yeah, so let's write Y is a set, such that A is a set, such that A has at least one element. So this set contains itself, because we know that a collection at least have one has one element exists, then this has at least one element, so it contains itself. Then comes our problem. What if we define X is a set such that B is a set, and such that B does not contain himself? So there is our starting point. Like, it's a paradox, like what we have seen. The question is X in X? Again, paradox, right? Because we don't know. Actually, we have it. What we have is a contradiction. Anyway, since if yes, that means if X is here, then X is not in X. Contradiction. If no, then if the answer is no, then X is in X, which is still a contradiction. So then we have our first paradox, like the problem of the definition of a set as just a collection of objects with some property. Because we can have this property, it's a well-defined property. So we have to redefine what is a set. So if Cantor saw this, maybe he was sad or maybe happy, I don't know. But the corresponding songs for that is oh, in my hand. Actually, okay. So that may be what Cantor feels.
The black group was soft before.
Oh yeah, they're so strong. Okay. Okay, so now we have to, since we have a problem from the definition, from the belief what is set, then we have to redefine set by setting some axioms, but we can believe it's true. So first of all, we have like 9 axioms and 10 with the axiom of choice. We're not gonna discuss about them all, but it's gonna take our time. But the first axiom we need is like axiom of extensionality. It's like two sets are equal. So now from this, we have that this cannot be a set. These things, which is a collection of such objects, and we call those class. So class is a set, a collection of sets. So a set of all set is a class. We define it like that. But a set is let's think about it like a small collection of objects with some property that we can find here, like from example. So we say that two sets A and B are equal if, so what I mean here is if they had the same element. So to show that two sets are identical, we just show that they have the same elements. So that is our thought. We don't need to prove that because it's an axiom. So we just assume that it is true. So our second axiom is for any set. I mean, like that. Okay. So the second belief that we have is there exists a set with no member. There exists a set with no member. So we call it empty set, has no member. And by the first axiom, we have the unicity of such a set because we cannot. So this is quite nice because it has no element. So every set that has no member are the same. And that is quite nice because let's think about it like the set of all elephants in this room is the same as the set of solution of x plus 1 equal 0 in the real number. So they're the same. Yeah. Math is nice, right? Okay. So another axiom is like, yeah, I'm just gonna talk about them because we're not really. So from a given set, we can construct another set by taking the elements of that set with some property that we want. And those things are, it's like a subset. So how to define a subset? So we need to find that subset is just a set, like in which, let's say, we denote it B is a subset of A if every element in B R implies X in A for every element in B, then the element is in A. So it's a subset. Okay. And for the next section, like we can construct from two given set, we can construct a set which contains those two sets. We can construct the union. Union is like a set but contains every element of our given set first. And the power set, which is interesting. The power set is a set, like it's given an axiom, like a power set is a set of subset of a given set X, let's say X. Like S such that S is a subset of X. And then there are still few axioms, but what we need is like the power set, the axiom of extensionality, and the empty set. So we will gonna use them. So first of all, we're gonna define order pair AB to be the set such that A, and we are going to define a Cartesian product like A times B, in which elements are order pair A, and B. So if two order pair are equal by the axiom of extensionality, you can show that they have the same components, like A. We can show that. And from this Cartesian product, we can define a relation. So a binary relation is just a subset of a Cartesian product. So we say a binary relation R is just a subset of Cartesian product. And then the interesting one, but we're going to use all one to talk, which is a function. So I'm going to. So a function is actually a subset of Cartesian product with some rules. It's a relation, but we have some rules. So let's say A, and we send elements in B. So we have some elements here. And the rules we have is like if each element here must correspond to one element here. Yeah. So one element here cannot correspond to two elements here in B. So that means we take an element and we send it here, call it like evaluation. We evaluate the element of A. And maybe it's possible to have this. And it's possible, but some elements here does not correspond to some elements here, but every element here must have one element here corresponding to that. That is the rule. And we call that function. It's a binary relation, but with some special rules. And then we have, this is like, we write it F from A to B, and like we take an element here, and the notation is like F of A. So some property that we have, we say a function is injective if one element here corresponds in one element here. That means they don't have this. And we call here image. We call here dissident. So every element here have unique. So two different elements have two different image. That's how we define. It's possible, but some element does not have. We call that gray image. What we have here does not have gray image, but each element must have one corresponding to it and not to others. And this is injective. And surjective, we have. We call it surjective if every element in the image in the name. So here we call it domain, and here we call domain. Every element in the codomain had some gray image. That means there are some elements in the domain. Maybe. Okay, so every element here has some elements of that, which every element here is an image of an element here. That's maybe correct. So we're going to need that later. But what we need to define is what if we have the function like we have A, B, C. So we have, let's say, F and G, and we call it the composition. It's an operation on the function, like we know, like from this to here as G, F, in which take an element here directly here. That means we can put like, yeah, we can play from this. So we can say that this is sent here, and this is sent here, and this is sent here. That's what we redirected. Yeah. And the last property that we need is the identity map, which is we denote it like 1A or B. A. Let's say it has 3 elements and 3 elements. So it just send every element to each sub. So we're gonna need it to when we define category. So function is defined when we're in high school, like from a real number to real number, and we have some nice graph. I think everybody saw that. Like, for example, if we take this is the real line, and function which take x or y. Let's define this is y, x, y equal to x. We have this, and maybe we're not making really boring. We're going to make a tensor function for some 2 seconds, maybe. Are you agree with that? Tensor function. Okay. So, or since we define what is a function, let's make like the following pattern. We're gonna follow those. They corresponding. This is y equal to minus x, y equal to x, y equals to the absolute value of x minus absolute value x squared x over 3. Okay, let's say. So it's something like this. Actually, what I mean here is 1 over x. Like properly, and I still need some space. So what we're gonna do is like we're gonna follow those pattern. It's like yeah, it's like this, that, and it's like yeah, it's hard for a little bit. That and that, yeah, that and that. Yeah. Maybe hopefully we can. So let's dance. Hope we can do it. Okay, are you ready? Did you hear that? Okay. But anyone want to dance? Come on. Okay. Fine. Yeah, so that means even the function with abstract sense, we can always play with it. Okay. So now we are going to the talk today. Okay, so now we can define what is a category theory. So a category, what do we mean about category is just, it's a collection of mathematical objects. What we mean by object is like a set, a groups, arrays. Yeah, we take those object and we call it class of object because it may not a set as we See, but there is no set of all sets. So a collection of all sets. We can form a category from that, and we define a category. It has objects. Let's note A, B, C, and yeah, and it has an arrow between the object. So it's just a relationship between the object, like what we did, like binary relation. Arrow, and the way you can note it like F, G, and anything like that. But this arrow, it cannot be like any relation. As we defined here, as the property of function, it must be well defined. So what we have is like this arrow must satisfy some property, like there we have the first operation of the domain. We define this as operation domain of the arrow and codomain of the arrow presentation. And those things must be an object of a category. Yeah, so it's just a definition in abstract sense. And then from that, we have identity arrow, like we denote the arrow here, like F from A to B, for example. It's just a notation. So identity sends A to itself as what we have in function. And it must satisfy some law for composition law. Which takes, if we have two arrows in which the codomain of the one is the domain of the others, let's say as we have A, B, C, this is F, and this is J, then we can define the composition such that J, we take J as first composition, F is A to C. And we have the associativity of this law, associativity which takes G, so F, certain H, equal to. So whatever order you take first, you compose first, it's always the same. G, rho, F, H. Okay. And the identity of the unit play the role of one in multiplication, like 1 times 2 is 2, 1 times, or 2 times 1 is 2. So the identity is like our identity here composed to any arrow, like for example, composed to J. Let's say identity of B composed to J is J composed to like identity of C. So, and it's still J for any arrow. So it's played the role of 1. So if we have such object and a row which satisfy that property, we have a category. Yeah, that is just a definition. It's not a big deal. It's a new math. It's so simple. So now, what I want to define is what means same thing in a category. So we say two objects are the same if we multiply if there is an arrow like A to B and B to A F G such that the composition G means G is an identity and G F. We say A and B are isomorphic, but in a categorical point of view, they are the same. So in set theory, same things means they have the same elements, but in category, they have this arrow which satisfies that property. So now we want to use that property in set theory to forget about elements. So you see, the definition is really simple. Now we're gonna play using those properties in set theory. yeah, it looks like an angel, but what hiding behind is really a devil, like the following song. You have an idea of the song?
Look like an angel. Walk like an angel. Talk like an angel.
It's a language category.
The sky, orange tomorrow.
Okay. Yeah, it looks like an angel. It's just that. But what hiding behind is really, yeah, interesting. Okay. So now we want to axiomatize set theory using this property instead of the one we use first, the one I defined first, like using the element would like X have an element or something like that. So what we need to check first is like if we take a collection of all sets and we take the object as sets and the arrow as functions, is that a category? That's the question. So what we have as axiom, what we need to define. Like you take set S is a category. What I mean by S is the sets, we name it set with object sets and a row function. Actually, it is because we just take every set as object and a row as function. And as we saw that the function satisfies those properties because we have a composition of function and we can have this associativity. You see? So it is. I think we don't need to waste more time on that. So our second axiom is S has a terminal set. And I'm going to find what I mean by terminal is a set, like, one in object of S. Yeah, one an object of S, such that for every other object of S, there is a unique map from X to 1. So to define the equivalent of elements from the set theory, we have to define this axiom. And what we have is like for any X, we have this as there is a unique map. The question is, we have that from in a set, like if we have a set, we have this unique map to one object, and what it is, if we have it. Any idea? What plays the role of this terminal set? We call it 1. Sorry?
Yeah. Any set with what one element, right? No, not the empty set, because the empty set would be like
yeah. So if we send any set, if we define a function X to be empty, that means is there? Yeah. So it's it's fine. Yeah. Maybe we should talk about it. It's of course that X must be empty. So
any set with one element.
Yeah. That's okay. So any set with one element, and the nice things about that is since by this definition or of same things, any set with one element, we can always find a by two maps but satisfy this property. That's we call them isomorphism. Isomorph. So any set with one element are the same, and we define them as one. So let's say you take A to any set. So this is an arbitrary set. So the only possible function here is that every element here has as image is A. So that is unique. We have only one function, and that satisfies the story. So our definition now is let's define element. What we mean by element is any mapping or any arrow that's the element of a set A is whose codomain is A and domain is 1. So that's how we're going to define an element now from now. If we mean about elements, it's just an arrow. It's not an element, like you said, but it's just an arrow. So that's the reason we need this one. So actually, still have a few minutes to work on it. Yeah. And then what plays the role of empty sets? It's just now we have another axiom because we need to have the empty set. That means we have the initial object exists. And what I mean by initial object is, let's denote by 0, an element O in S such that for any element X in S, there is a unique arrow from that element to S. And obviously, if we take the set with one element as what we did, we don't have a unique mapping. We have many mapping. See? So the one later is the empty set, but let it go. So now we have the axiom corresponding to empty set for this. And so now we can see that what we mean by element is a special case for a row. That means if we want to evaluate an element, we evaluate an arrow, and evaluation at that point is just a special case of composition because it's two arrow, but we evaluate, and evaluation of composition is a special case of associativity. So now we define everything in the set as just from the category theory. And then the next axiom, what we need is we must set this axiom. It's not. So the initial object cannot be the terminal object. Yeah, so in some of a category, like category of groups, we have equality between those two things. But in set, if we have a category and we define this category as a category of sets, then it has to satisfy that property. So what interesting is the construction. The construction of a sum, because if we have two sets, we have like the union of two sets. So what we mean by sum is like if we have sets here of the X set. So we want say from those two small sets, we want to construct this big set, according to that, and how to axiomatize that one. So we define. So we can first start by the set of two elements. So the way we define it, like for any set, we for any given set, A1 not and A1, we say A is A plus A1 plus A not plus A1. If we have the following property, let's make it by a rule. Okay, no. A1. So if we have an arrow from A0 and A1, and we have another set, but there exists this arrow, then there exists a unique arrow from this list. So we must have the following property, then this one called sum. And actually, if we go back to set theory, it's going to be the disjoint union of this element. That means they are exclusive, and every element here is here, every element here is there. Actually, we don't have a lot of time anymore, but it took more time as I thought. So actually, my goal is like, as I told you, I cannot do all of this today, but the goal is to construct an axiom of set from a categorical point of view. As we saw, what we saw today is like we can find, we just said, but this S must be category, which contains the object or sets, and it has a terminal sets. Some category doesn't have it. It has an initial, and we call this one non-degeneracy. So if a given category satisfy that, so it's gonna be the category of set. And in the general axiomatization of such a theory is like what I want to show is like, but 9 axioms of set theory can be embedded in 3 axioms from category theory, such that it must have all finite limits and finite limits, and those things are like a kind of just a type of arrow, but we don't have really time to define it, and it must have the second axiom is like we have the exponentiation of that in that category, and we can define for the third category, for the third axiom, we can define truth objects. So each that 3, maybe next time I will have time to discuss about them all. But the nice things is like every category that satisfy those property, we call them topos, and it's a generalization of space. So in my previous master, I worked on a special kind of space, and it's really interesting. It's surely abstract, but the good things using categories about the computability, because, for example, in computer science, what you use is a kind of function, because you write some code and we call them. So it's kind of function, and a categorization of set theory, make it more computable. So what I'm doing is a kind of translation from one language of theory to another language of theory. I think I'm going to stop here today. If anyone has a question.
Yes, questions?
Do you know if there is any limit of the objects that you can have? I'm particularly interested in. Can objects be like logical statements written in another logical language?
Yeah, so since the Boolean algebra, it is the algebra of proposition, assuming the object is the same. So what if, because you can define from a Boolean algebra, you can take all object as a Boolean algebra. So what if you take that kind of category?
So they are not only mathematical objects, but they can be logical objects in general.
Yeah, so what do we mean about not mathematical?
Yeah, like, for example, not necessarily classes or sets as the ones we know, but
Oh yeah,
maybe like
so yeah, that what I mean. So that's what I mean by, because if we try to axiomatize set theory, because actual mathematics are built from set theory, you know, and what if we build something not from set theory? So what must satisfy the foundation? And by axiomatize set category of sets, we have such a property, a generalization, but any alpha category satisfying, we call it topos, and it may be not a set, but a topos.
Other questions?
But it's going to be mathematical because we define such.
So your arrows have to be associated. Can categories describe things that are non-associated?
Actually, by the definition. You mean the arrow? By definition, no. So the arrow must be associated.
Other questions? Okay, let's think of bigger again. Well, thanks for turning out. Rule math club is all pieces gotta be gone, so if there's any less, take it. I hope to see you all next week and have a great weekend.